All right. Hi. My name is Aiden Seung Lee, and I'm from Brown University, and I'll be talking about our paper, deep learning based approach for automatic VR image upright adjustment. As you can see in various platforms such as Facebook or Google Street View, more and more VR images and videos contents are coming out every day. I mean, this is due to the large various type of VR 360 cameras coming out from the industry. I mean, these cameras capture VR images and videos that can be later be used in the VR headset. When we use the VR cameras, they're usually fixed to a pole or stick so that the captured VR images are always vertically upright. However, there are cases where the pole or the stick that is connected to the VR camera is tilted, like the picture on the right, which causes heavy VR sickness when the user sees these pictures while wearing the headset. So our goal here is to automatically ratify these rotated VR images to be vertically upright. Previous attempts include manual ratification using programs such as Adobe Pro, hardware such as gyroscopes, or utilizing computer vision methods such as horizon-based or lines-based. However, these all have limitations as specified in the slide. Specifically, computer vision methods usually fail to generalize to the general scenes as it requires specific features in the images. So recently, deep learning approach has been applied, but they mainly focus on the standard non-VR images. Now I'd like to elaborate on our approach. Our approach can be divided into two steps. The first step would be to create a large-scale rotated VR image dataset with the label as the ground truth orientation. Manually creating a dataset that contains rotated VR images and its orientation is a very hard process, as it requires all types of orientation, and deep learning these requires lots of data. Therefore, we synthetically rotate and create the dataset from the upright images. Since we synthetically rotated these images, we now have the ground truth orientation for the labels. Using the spherical coordinate system, phi and theta, or azimuth or angle elevation in top left, we can get a very large set of rotated VR images from an upright image. We then use this large data set as the input to convolution neural network and set output as their ground truth orientation vector. When the model successfully outputs the orientation vector of the rotated image, we apply the inverse rotation matrix of the orientation vector to get the upright images. For the deep learning, we tested various architectures such as ResNet 50, Inception V3, and DenseNet 121, and evaluated the performance. For the loss function, we utilize a log cost function instead of the traditional L1 or L2 norm, as it has shown to give them better performance in regression problems. And for the distance or error definition inside the norm, we investigated two different types. The first is what we call the angular difference, where we try to minimize the sum of the distance of each angle phi and theta. The second is what we call geodesic distance, where we try to minimize the distance in terms of vectors, the predicted and the ground truth in the sphere. We also investigated three ways to account for the output angle, as the network can predict angles outside of the angle range. Before we dive into the results, I want to explain the challenges that we faced when we trained the neural network. The first problem we encountered is the creation of the rotation artifact when we synthetically rotated the images. Rather than learning the rotation itself, the neural network appeared to learn these artifacts and failed to predict well on the naturally rotated images. The second problem that we encounter is the limited number of training images. Since we only had 35,000 unique images from MIT Sun 360 dataset, we have to make sure if this is enough for the training. The third problem is the training time, as it is computationally expensive and time-consuming to rotate and remap the VR images on the fly. To overcome this constraint, we actually discretize the rotation space and fix the number of orientation vectors for the rotation. Now let me dive into the results. These are the results of different configuration of the network and for the problems that I just mentioned above. I mentioned before, excuse me. If you look at the result for the different types of CNN architectures, we can see that the DenseNet provides the best performance out of the other two remaining architectures. This is natural, as DenseNet performed better than the two network structures in the regular image recognition tasks. The bottom figure shows the results for the loss function. Overall, the angular distance definitions gives much better performance than the geodesic distance, regardless of the geodesic distance definition, regardless of the output angle bounding method. We can see that the way we define the error or distance is much more important in performance, as it directly impacts the loss function. It is interesting how unconstrained output handling method gave the best performance in angular distance definition. We can predict, what we think is that the network actually predicted angles close enough to the actual angle to ignore this angle constraint. This is the result to handle the rotation artifact. We found out that the downscaling before the rotation mainly causes the rotation artifacts, because the downscaling itself corrupts the image greatly. But we couldn't ignore the downscaling part because it is required for the training, as it is computationally impossible to train large size images. Therefore, we minimize the rotation artifact by downscaling and rotating at the same time, which we called combined mapping. The specifics are in the paper. As you can see in the figure, the green line, which represents the combined mapping, performs much better than the blue line, which is the result due to the rotation artifact. And unlike our concern, we see that 15,000 VR training images were enough, as there is no significant performance gain when the number of training VR images exceeded 15,000. To reduce the training time, as I mentioned above, I said that we fixed the rotation space. Since the real-world rotated VR images are in the continuous space, we can infer that the discretized or fixed rotations during the training can deteriorate the performance in the real-world application. However, when we conducted an experiment, we can see that there is almost no performance gap between the 10,000 up vectors, or 10,000 different rotations, and 50,000 up vectors or rotation types. In other words, when the number of up vectors or rotation types exceeds certain numbers, in this case 10,000, it does not affect the performance greatly. But we gain lots of computational. We get a huge gain in terms of the time and computation. The last figure is the heat map, and we can see that the network gives constant results to all types of the orientation vectors. One of the interesting results is when the elevation is 180 degrees. We can see that compared to the other parts, there are some bad results here, and this is due to the fact that upside down images, which means elevation is 180 degrees, are very hard to predict, as they are already vertically upright. We will see those cases in the upcoming failure cases slides. Before I wrap up our performance result, we have to quantify how much error is good enough, since we are producing the values instead of classes. Therefore, we conducted a user study to quantify the human perception of vertically upright images. Based on the user study, we will use 5 degrees for very satisfying upright images and 12 degrees for just regular satisfying upright images to measure the performance. Using the best combination of configurations from the experiments, we achieved 90.27% accuracy for very satisfying upright images and 96.36% accuracy for satisfying category VR image vertically upright images. Since our method can handle all types of scenes, it is robust to most of the scenes, and it still gives constant accuracy results. Now let me show you some actual results. For each pair, left is the input image and right is our ratification result. These scenes include indoors, outdoors, urban, natural, upside down, blurry images, different cameras, and ground to aerial views. Excuse me. As you can see, the network gives constant performance to all types of scenes. Comparing to the previous approach, mainly line-based and horizon-based, we can see that it still shows much better, much more consistent output to all types of scenes. We also conducted the user study that backs up that our method outperforms the line and horizon-based approach. And one of the interesting things here is that when we tried to reproduce the line-based or horizon-based approach, it took almost 30 to 50 seconds per image. Our network can be quick as 50 milliseconds per image. So in times of time, it also gives a much performance increase. Our approach can also be used in the 3D reconstruction, as 360 cameras are utilized for 3D reconstruction, and it can also be used in cases like 360 videos. Now let me show you the failure cases. We found out that most of the failure cases fall into two categories. First is when the image is vertically upright but are upside down. This type of problem is extremely hard to predict for the neural network since it can be viewed as already vertically upright. The second category is when the image is taken in the top-down view. These kind of pictures are hard for even humans, as there are literally no features of vertical and horizontal lines, and all the stairs and the contents are tilted. In the future, it will be interesting to train a neural network that can handle these type of scenes as well. In conclusion, as far as we know, our approach is the first deep learning-based approach for VR image upright adjustment. It is robust to different rotation types, upside down, cameras, and scenes. We also find a way to create a large-scale dataset for training VR images with ground truth orientation labels, if we have the upright images. And we are also planning to upload the code and make a demo website so people can test this out. I would like to make an acknowledgement to these institutions for funding our research. And yeah, let me finish up by showing you more results. Thank you.
Great, thank you. We have time for one or two questions. And I can start us off. Do you have any thoughts about other types of camera parameters that you might be able to estimate using this methodology?
Camera parameters?
Right, for example, projection, intrinsics, or other aspects of scenes that you might want to estimate using a neural network like this.
Sorry.
Yeah. Yeah, it will be really interesting, but we still have to find a way to create the data set for the training. So I think the key point is to try to find the right way to get the data set for the training. Yeah.
Sure. I could ask you one more question, if you don't mind.
Yeah.
Do you, so this was synthetically generated data. Do you have any evaluation on actual not quite upright images?
Right. So if you look at the pictures on the 6th row or 7th row, those pictures are data set from the pictures that are taken by actual people. So we tested out if it actually works on the real world data set. And one of the challenges that we faced was the thing that you just mentioned. It doesn't work on the real world data set. And it was largely due to the rotation artifact created by the synthetic rotation. So we managed to figure that out, and yeah, it worked.
Okay, let's thank the speaker again.